Good morning, everybody. This is going to be our second podcast of Chapter 11, and today we're going to talk a little bit more about solubility. We did this in the last podcast where we talked about what it takes to dissolve something. And this chart right here that we're starting with is a little bit of a summary of that. And if you can take a look, again, we talked about, we know what over here polar solutes. Let me grab a pen here. We know what a polar solute and a polar solvent, remember that it has uneven charges, like dissolves like. If I start here, polar dissolving in polar, that should make sense way over here that my solution is going to form. Non-polar, remember it has even charges all the way around it. A polar solute and then a polar solvent like water, that should make sense to you that they don't want to dissolve in each other because like dissolves like. Here I have non-polar solute, non-polar solvent. Yes, a solution should form. And then we have a polar solute and a non-polar solvent. Again, no solution is going to form. So again, just keeping in mind the expression that we're using, that like dissolves like. And again, to remember the change in heat of the equation 1, if you remember, this is where we want to separate the solute. So make sure you're jotting this down that we want to separate our solutes. And then in equation 2, we need to expand our solvent so that we can get some space in there and we're able to get our solute into that. So we want to expand our solvents. And then in step 3, that's where we have the interaction between our solute and solvent. So as we were talking about with like dissolves like, whether or not it's going to form a solution, if energy is going to be released or not. And then we're talking about the sum. So this is the sum of our heat of our solution. So in terms of large and negative and small, remember the negative means that it's an exothermic reaction. If it's positive, that means it's endothermic and heat is being taken in. If I have large and small here without any idea, you have to address it to the type of solute or solvent that you have, whether it's going to be endothermic or exothermic. Now this is all in terms of solubility and if things are going to be able to dissolve in one another, and of course there are some factors that play a part in that. And we kind of talked about this on the first day when we were looking at this class, or this chapter, that the structure effects, a nonpolar dissolves nonpolar. The easiest thing when you guys are thinking about a nonpolar substance, always just be thinking about methane. It's the simplest structure for you to draw, and if you are trying to give some reasoning, you can easily draw it. Everyone knows what methane is, and you can see that it's easily nonpolar, and it doesn't have any excess charges, and so the only bond that you have to overcome between the two structures, hopefully you're thinking this to yourself before I even say it, is London dispersion, sorry that's an H, London dispersion forces. So those London dispersion forces, as we talked about before in the last chapter, are very, very weak. So there's not really an attractive force here. The molecules are able to slide and move around with each other, something that's going to affect solubility between two nonpolar solvents. Now if I take a look at polar dissolves polar, hopefully you're thinking about water. That's the most common polar substance that you should be thinking about, and you guys know by now that the hydrogen end is slightly positive and the oxygen end is slightly negative. And if I combine that with another polar substance like hydrochloric acid, you guys should recognize that the chlorine end is slightly negative and the hydrogen end is slightly positive, and so we have this attraction between these two. And I hope you're thinking to yourself that that is hydrogen bonding, and that should be stronger than what we just talked about here with London dispersion forces. So yes, we have attractive forces here, and that's going to affect some of my solubility. And then we have polar and nonpolar. Well, you should recognize that, again, polar. I always think of water as a polar molecule, and if I look at this polar molecule, again, I have uneven charges, slightly positive side, and then I have water that has the slightly negative side. And if I take something that's nonpolar, like we just talked about with methane, remember it's just the one that you should have as your picture, it's easy to draw, easy to remember, there is not going to be any attractive forces here. This one is stable, the tug of war, no one's winning it, it's completely satisfied, and so there's no attractive forces. This is not going to be able to dissolve. Now another thing that we haven't talked about yet is pressure. Pressure is greatly going to affect whether or not solubility can happen. We haven't talked about STP or anything like that yet. So here this is going to come into play. And this is greatly going to come into play for gases. Pressure, there is no effect for a solid or a liquid. So write that down. There is no effect for a solid or a liquid. Take the pencil that you're probably writing with right now, on the paper that you're writing with. It doesn't matter if you apply more or less pressure, you're not going to get something to dissolve more. You might break something, but it's not going to affect its solubility. Now for gases, pressure greatly affects how well something is going to dissolve. And so for gases, the general rule is the greater the pressure is, you can say the greater amount of gases that are going to dissolve. And you can think about this if you are an athlete that is training up in higher elevation. There isn't as many gases that are going to be dissolved there. You're at lower pressure, and so your body has to work a lot harder to perform in the manner that you want to perform. Then you come back down to Hastings, Minnesota, and there's more molecules in the air, there's more ability for you to take in those gases, and you have a lot more endurance. So a lot of times you hear those long distance people training at higher elevations so that when they race down at lower elevations, they perform much better. Now you might need a little bit of a new page here, and so I'm going to put in a new page here. So I want to talk a little bit more about pressure, and I want to introduce Henry's law. So Henry's law has to do with pressure. So go ahead and write down Henry's law, which is a little bit harder for me to do here with my pen. So Henry's law takes into account pressure, and it also takes into account the concentration of the solution that we are taking a look at. So he basically said that the pressure is going to be proportional to the concentration. Now we just talked about in the last section that concentration can be in the form of molality, molarity, normality, percent by mass. There's all kinds of things. The two mainly that we're going to be taking a look at is molarity and molality. But if you guys can take a look at this, we have pressure that's proportional to the concentration of my solution. He further took a look at that this concentration is equal to some sort of constant times whatever pressure that you are at. And I think the best way that I can explain this is if you think about a soda can. A soda can has this teeny little lip right here, and then you have the rest of your can. Let's see, not too bad. For me, it probably would be a little Diet Coke. Okay, and we have our little tab right up here, and we know that when we open this up, we have carbon dioxide gas that's going to come rushing out of here. Well, how do they get so much carbon dioxide gas? Well, if we talk about that the greater the pressure is, the greater amount of dissolved gas you can get in there, you should be saying to yourself that, well, they probably increase the pressure. And you're exactly right. What they try to do, they try to bottle this at a higher pressure of like 4 atmospheres. And what actually happens here, the reason that all cans have this little lip is for the most part, inside the can here is going to be 1 atmosphere. Here, because of that slight indent, we can say that it's 1.1. We can increase the pressure. Just that small amount allows them to dissolve more of this carbon dioxide gas into here. Now, it's not really dissolving. They're forcing this to happen because if you think about carbon dioxide, this is a non-polar solute. Non-polar solute trying to get into water. And you guys know that water is polar. Well, that really shouldn't mix. So the minute you open this, this gas is going to rush out because there's so much pressure inside of this container. They've actually created a super saturated solution. So when I increase this and I open up my tab, it should make sense to you that my pressure is going to go down. Well, my carbon dioxide is releasing, and so what also goes down is my concentration. And so it's a direct proportion again, like Henry's law is showing. So let's think about this one more time. If I get this carbon dioxide out of here and a little bit of time has gone past, my Diet Coke is it's probably going to taste a little flat. It's not going to be as good anymore. But what actually happens, if you remember your pH scale, pop is down here at a 1 or a 2 when it's bottled like this. As that carbon dioxide is released, it becomes less and less and less acidic, so the pH actually goes up the longer your pop sits there. So if you've ever had to drink flat pop because you've been sick and your mom says it's the best thing that's for your stomach to settle it, she's actually right. It's increasing the pH as it's sitting there. So our stomach acid is more like this. If we're drinking something that's flat or has a higher pH, it's actually neutralizing or settling our stomach. And as our mom may say to you, well, it's just good for you. I'm not sure why, but just drink it when you really don't want to anyway. Okay, so pressure does affect solubility. And then the last thing that we had on this page was temperature. Well, gases, if pressure is greatly affecting gases and that's affecting solubility, you should be thinking that temperature is going to do the same, because temperature and pressure are both greatly affected by gases. So if I think about the solubility of a solid in a liquid, so we are just talking about our regular old Kool-Aid that we've been using all along. Well, then our diagram is going to be like this. If I talk about the amount of grams that I have in degrees Celsius, we all know that if I increase the temperature of my water or my liquid, whatever it is, I can dissolve more solid in there. This is the environment that we often live in. This is the one that we have studied at home in our kitchen, making candy or whatever you guys are doing. Well, then the next one, if we take a gas, and that's going to be dissolved in a liquid. So again, my carbon dioxide dissolved in my liquid water to make my Diet Coke, that's actually going to act in the opposite direction as I increase the temperature. So the mass of the gas over the temperature is going to decrease the solubility as I increase its temperature. So they're exact opposite of each other. Okay, so that is section 11.3, and you should be able to do a couple more problems now, and we have 2 more podcasts probably to get through this section. Have an awesome day.